In this video, we're going to start going into more detail on nucleophilic substitution reactions. And if you remember from the last video, nucleophilic substitution and then also elimination reactions were common types of reactions that alkyl halides undergo. The remainder of chapter 7 will be focused on nucleophilic substitution reactions. So remember what we're doing here is we're taking our alkyl halide, and then just also as a reminder, right, this R is a carbon-based group, and that carbon does need to be sp3 hybridized. So I do need an sp3 hybridized carbon, right? If it's sp2 or sp hybridized, it's not going to undergo nucleophilic substitution reactions. So if we had a vinyl halide or an aryl halide, again, I would get no reaction here. So sp3 hybridized. And then remember that that carbon is also partial positive because of the bond to that halogen, right? The halogen is more electronegative. It's more polarizable as it gets larger. So I'm taking that alkyl halide, and then I'm going to react it with a nucleophile. I'm putting a charge on this one, but it doesn't have to be charged. It could be neutral or charged. So charged or neutral. By neutral, I just mean electrically neutral, so something like water, right? There's 2 lone pairs on oxygen. Water is nucleophilic, but it is uncharged. So charged or neutral nucleophile. And we're going to then end up substituting. So the nucleophile will replace the halogen. So my carbon-based group is now bonded to the nucleophile, and then my halogen. It had 3 lone pairs, it now has an extra lone pair. Some terminology that goes with this, we're going to call that halogen my leaving group. So whether it's attached or by itself, right? This is the leaving group before it left. This is my leaving group after it's left. So some terminology that I'm going to use alkyl halide, right? So that's my Rx. I'm going to use nucleophile, right? That's what's going to be attacking that partial positive carbon. And then my leaving group is what's going to be leaving, right? We're breaking that carbon halogen bond. So we're breaking the bond between carbon and that leaving group. My leaving group is leaving. So 3 necessary components for a substitution reaction. The alkyl group, so the carbon-based group that's attached to that halogen, my halogen, right, my leaving group, and then the nucleophile. So 3 necessary components. The alkyl group, right? That's the R part of my Rx, right? The sp3 carbon that's bonded to the halogen. My halogen also called my leaving group. And we're going to abbreviate leaving group capital L, capital G. So my leaving group, right, it's going to accept the electron density from that carbon-halogen bond. If we go back up and look at that reaction, right, I had said originally it had 3 lone pairs, and then once it is left, it now has 4 lone pairs, right? That extra set of electrons is coming from that carbon-halogen bond. So it's accepting that electron density. Better leaving groups are going to be groups that can better handle that negative charge, right? It can handle those extra electrons. So my leaving group, it accepts the electron density from that carbon-halogen bond. In chapter 9, we are going to look at some substitution reactions, and we're going to have leaving groups that aren't halogens. In this chapter, they're going to be halogens because it's on alkyl halides, but leaving groups don't have to be halogens. They just have to be able to accept that electron density. So, better leaving groups. Can better accept that electron pair. I don't know if can better is proper English. Can best accept that electron pair. So they can stabilize that better. It's actually leaving group, and we'll talk about this coming up, but the better the leaving group, the weaker the base, right? Bases, if we think Lewis bases, they want to donate electrons. My leaving group wants to keep those electrons, right? It wants to accept them. So better leaving groups can better accept that electron pair. And then I mentioned this, but we'll write it down too. We can have other leaving groups that aren't halogens. In this chapter, they primarily will be, but they don't necessarily have to be. So we can have other leaving groups besides halogens. Just kind of an example. An alcohol, we're going to see these in chapter 9. We're going to end up protonating it first, so I'm going to add a proton to it. But then that is going to leave, and we would end up with, I'm not going to draw the whole reaction, but I end up with water as my leaving group. So water is a leaving group. N2 is another one. So if I have a nitrogen with a triple bond to another nitrogen, that can leave. And then we can end up with N2 as my leaving group. Again, these aren't balanced. I'm just showing the leaving group portion. And then my third component is my nucleophile, right? We're breaking our bond, right? We're doing a substitution. So I'm breaking the bond between that alkyl group and my halogen. And then I need to form a bond between that alkyl group and my nucleophile. So number 3, the nucleophile. And again, we said it can be neutral or charged. It does have to be nucleophilic, however, so it does have to be electron rich, right? So it either needs to have a lone pair of electrons or a pi bond. We should say pair. We're doing polar mechanisms here, not radical ones, right? So a lone pair of electrons or pi bond. So it can be neutral, but it still needs to be a nucleophile. So we're going to look into a little more detail on all 3 of these components. So my first one is my alkyl group. And for this part, we really just want to be able to look at the alkyl halide and see, is it primary, secondary, tertiary? Is it allelic, benzylic? Is it a vinyl or aryl halide? If it's vinyl or aryl, again, it's not going to undergo nucleophilic substitution or elimination reactions. So when we're looking at our alkyl group, we're really looking at the alkyl halide, and we're just saying, okay, what degree is it? So our alkyl group, really our alkyl halide, but just focusing on the carbon portion. So this part of it. And again, just kind of a review from our first video, primary alkyl halides, my carbon, and I'm just going to draw examples. There's other examples, right? But my carbon is going to be bonded to one other carbon. So the carbon that my halogen is bonded to one other carbon. Is it secondary? My carbon that halogen is bonded to two other carbons. Is it tertiary? The carbon that halogen is bonded to three other carbons. And of course, these are just examples, right? I could go and I could make them big and messy. I could put some rings on here. I could do all sorts of crazy things, right? That would be a primary alkyl halide because this carbon is bonded only directly to one other carbon. And again, we covered those in the first video of this chapter. We also had allelic halides, and those were ones where we had a multiple bond adjacent to the carbon that's bonded to that halogen. Benzylic, keep on wanting to put two L's in benzylic. So we had our benzene ring, and then a carbon, and then the halogen. Again, the halogen is not bonded directly to the benzene ring. If it was, it would be aryl or arylic. And in that case, right, my carbon that the halogen is bonded to is sp3 hybridized. I'm just going to draw it a little bigger. I started getting really small on you. And then vinyl would be the counterpart to my allelic one. And again, that halogen is bonded to an sp2 hybridized carbon. So we want to remember that these guys are not going to undergo nucleophilic substitution reactions. And I'll totally give you one, right? We're just expecting you to write no reaction for our product instead of writing a product, right? This is sp2, this is sp2, right? We want an sp3 hybridized carbon bonded to the halogen. And then what is its degree, right? Is it a primary, secondary, tertiary, or is it allelic or benzylic? But what is the nature of that alkyl group? Our leaving group, so I had said a few minutes ago that better leaving groups are better able to accept that electron pair. So the leaving group is going to accept the electron pair. Better leaving groups are better able to accept that pair or stabilize the pair, if you want to think about it that way. So better leaving groups are going to be weaker bases. So better leaving groups are weaker bases, right? Remember, using our Lewis definition, bases, right? These guys are going to donate an electron pair. My leaving group is going to accept an electron pair. So if it's bad at donating it, it's going to be better at accepting it, and vice versa. So we want things that aren't good at donating them. We want things that are good at accepting those electrons. So using trends on our periodic table, basicity And again, remember, if it's a stronger base, it's a worse leaving group, and vice versa. Basicity decreases as we go left to right across the periodic table. Since basicity is decreasing as we go left to right, it's a better leaving group, right? So better leaving group. So if I was to compare NH3 to water to HF, right? As I go, let's put the arrow backwards this way. It's a stronger base on this side, right? Basicity is decreasing as I go in the other direction, which means it's increasing in this direction. So stronger base. Ammonia is a stronger base than water. Water is a stronger base than hydrofluoric acid. In fact, we don't even really think of hydrofluoric acid as being basic, right? Its conjugate would be. Which means as I go in this direction, it's going to be a better leaving group. We're not going to really see HF as a leaving group, but we could see an amine, right? Carbon bonded to nitrogen or carbon bonded to my water group. I also we could talk about a trend on the going down a group. So basicity decreases down a group. Of the periodic table. So leaving groups increase, right? Better leaving group. So if I was to compare fluorine to chlorine to bromine to iodine, right? As I go down, it's a worse base. So let's actually do what we did last time, better base. If you remember from 152, chlorine, right, chloride ions, bromide ions, and iodide ions we considered inert, right? They come from neutral salts. So we don't even think of those as being basic, right? If I was to write an acid-base reaction for HCl, right, my acid dissociation equilibrium equation, right? We form hydronium ions and Cl minus. We write an arrow in one direction, right? I'm not writing this arrow because my chloride ions are considered inert. If I was to write that reaction with fluorine instead, right, this is an equilibrium reaction. The one that I wrote first actually isn't, right? HCl is a strong base, which means my chloride ions are like not basic at all. HF, however, is a weak base. Fluoride ions are weakly basic, so it can go back in the other direction. So if you remember that trend from 152, it kind of helps to remember this one, right? Fluoride ions are basic, weakly basic, but they're weakly basic. Chloride, bromide, and iodide ions aren't even really basic, which means they're going to be better leaving groups. Fluoride is actually not a very good leaving group at all. Equilibrium is going to favor the products of a nucleophilic substitution reaction when the leaving group is a weaker base than the nucleophile. It's kind of a mouthful, so we'll write it down here. So equilibrium favors the products of a nucleophilic substitution reaction when the leaving group is a weaker base than the nucleophile. So again, just a couple reminders here, right? If we think Lewis, our base, and even if we think Bronsted-Lowry, if it's going to accept a proton, those electrons that it's bonding to that proton with are coming from the base. So regardless, my base is the one providing those electrons. So my base is going to be an electron pair donor. A nucleophile, it's electron rich. It's also an electron donor, right? We draw the arrow from the nucleophile to the electrophile. It's my electron-rich site. My leaving group is the opposite of both of those, right? It's an electron pair acceptor. So my base is donating electrons. My leaving group is accepting electrons. If we're going to actually do a substitution, my nucleophile needs to be a stronger base than that leaving group, right? We want the nucleophile to donate the electrons, not the leaving group. We want the leaving group to be a weaker base, that's how I wrote it up above, than the nucleophile. We want to make sure the right one is donating the electrons and the right one is accepting those electrons. Otherwise, we're not going to get a substitution to happen. So an example, if I was to look at this alkyl halide, so chloroethane, 1 chloroethane, and then I'm just going to add hydroxide ions. And we're going to substitute and get an alcohol functional group plus chloride ions. And in the forward direction, right? Forward direction. My nucleophile is the hydroxide ion, and my leaving group is the chloride ion. In the reverse direction, it's the opposite, right? In the reverse direction, my nucleophile is the chloride ion, and my leaving group is the hydroxide group. If I was to look at pKa's, remember pKa's are for acids, right? The A in that stands for acid. So we're looking at the pKa of the conjugate acid of these bases. So the pKa for water, right, that's the conjugate acid of my hydroxide ion, is 15.7. The pKa for hydrochloric acid, right? Hydrochloric acid is a strong acid, so we don't really have one, but we can calculate it as a -7, right? And then it's kind of weird because we're talking basicity and I'm giving you values for acidity, but remember, the stronger the acid, the weaker its conjugate base. So because my pKa for HCl is smaller, right? Smaller pKa equals stronger acid. There's a lot of remembers here. Smaller pKa equals stronger acid. And then we could say stronger acid, weaker conjugate base. We can conclude that my chloride ions, right, are a weaker base than my hydroxide ions, right? My reasoning on that is that this has the smaller pKa, so stronger acid, lots of so's here, so Cl- is a weaker base. Than hydroxide ions. right? Water is the weaker acid, so its conjugate, OH minus, right, hydroxide, is the stronger base. So then if I go up to this, right, let's go up to my directions here. We're saying it's going to favor the products when the leaving group is a weaker base than the nucleophile. So I want my leaving group to be the weaker base. And if I look in the forward direction, here, this is the weaker base, right? We just came to that conclusion down here, right? Chloride is the weaker base, so weaker base. If I go here, chloride is still the weaker base, but it's my nucleophile, right? We want the leaving group to be the weaker base. So in which scenario, the forward or the reverse direction is my leaving group, the weaker base, the forward direction, right? So the forward direction is going to be favored for this one. Let's go through another example. And this one we're actually going to do without pKa's. So I'm going to have an alcohol and then acetate ions. And we're going to end up doing a substitution. So I am replacing my hydroxide group with that acetate group, and then I have my hydroxide ions by themselves. So what I tend to do, the way I like to do it better, is I'm just going to look at it in the forward direction. Remember, I want my leaving group to be a weaker base than my nucleophile. So I'm going to look at it in the forward direction. If my leaving group is not a weaker base, then I know the reverse direction is favored. So instead of doing both of them like we did up here, where I wrote both the forward and the reverse, I'm just going to look at the forward, and then I know if it's not right for the forward, it's going to be the reverse direction, right? I only have two options. It's either going to go forward or reverse. So if it's not going to go forward, it's going to go reverse. So in the forward direction, right, my nucleophile is my acetate. I just wanted to leave a little more room here. There are lone pairs on that oxygen also. And then my leaving group is hydroxide. So then our question, right, is the leaving group a weaker base than the nucleophile? If it is, it's going to go in the forward direction. If it isn't, then it's going to go in the reverse direction, because it would be the opposite, right? In the reverse direction, my acetate is the leaving group. My hydroxide ion is my nucleophile. So is, right, hydroxide a weaker base than acetate? And I could give you Ka's, but we don't need them, right? Remember, bases are things that want to donate their electrons. And my acetate, if we look at it, it actually has resonance. When we were looking at acidity trends at the beginning of the semester, remember we said that the stronger the acid, the more stable the base. And one of the things that stabilized the base was resonance. So this nucleophile, right, has resonance. It makes it more stable. If it's more stable, it's weaker, right? It's not as reactive. So because this has resonance, right, my electrons are delocalized, it's less likely to donate them, right? Remember, it's not resonance structures that exist, but it's the hybrid. So I'm actually taking that electron density and I'm spreading it thin, right? I'm spreading it out over this entire part of the molecule. So it's not like it's between one oxygen and the carbon sometimes and then the other oxygen and the carbon another time, right? It's not like it's moving like we're drawing the arrows, but it's both of those places at the same time, right? Each of those bonds, if I was to measure the strength, is like 1.5 times the strength of a single bond, right? Somewhere between a double and a single. So because that has resonance, it is a weaker base, right? Bases want to donate electrons, and if you delocalize those electrons, right, think about it as spreading it thin, you're less able to donate them. So we could say our electron density is delocalized, right? It's less ready to be donated, right? It's involved in resonance. If I look at my hydroxide ion, right, those lone pairs are just sitting there. They're not spread out. They're not delocalized. They're local, right? We could say they're the opposite of delocalized. They're localized, right? They're just sitting there ready to be donated. So no resonance, stabilization, can more readily be donated, making it the stronger base. Again, remember, bases are donating electrons. Hydroxide ions are just sitting there. I can donate them. With my acetate ions, it's delocalized, right? It's spread out over half of my molecule. It's less able to be donated. So is my leaving group a weaker base than the nucleophile? We've lost our question here. No, it's not, right? My leaving group is actually a stronger base than my acetate. Stronger base than my acetate ions. So which direction is this going to be favored? It's going to be favored in the reverse direction. I'm going to favor it in this direction, reverse favored. Because in the reverse direction, my hydroxide is my nucleophile, right? The thing that's donating the electrons in the reverse direction more readily wants to donate them. And then the thing that needs to stabilize those electrons, my acetates in the reverse direction, is more able to stabilize them because of resonance. So in this one, my reverse direction is going to be favored. I do want you to look at a couple tables in the text, and these are the tables out of the 5th edition. I honestly don't know if they're exactly the same numbers in the 4th or 3rd edition, or the 6th edition for that matter. So this is out of the 5th. You'll just have to compare. I'm sorry. I only have the 5th edition. But there are 2 tables of nucleophiles. 7.2 is a list of good nucleophiles. So based on the heading, you can find your tables. Good nucleophiles. Sorry, not nucleophiles, leaving groups. I'm jumping ahead. Good leaving groups. And then 7.3 is actually a list of bad leaving groups. So please look at those tables. We can actually list some of the bad leaving groups here if you want. So under bad leaving groups, fluoride ions. We know that fluoride is a weak base. Remember, leaving groups, we don't want to be very basic. We want them to accept electrons, not donate them. Hydroxide is actually a strong base. It doesn't want to accept electrons. It wants to donate them. NH2- is actually a stronger base than hydroxide ions are. Again, it wants to donate them. I have 2 lone pairs on that nitrogen. 3 lone pairs on that one. Hydride ions, so H-, and then R here is a carbon-based group, so carbon ions, carbon with a negative charge, also having a lone pair on it. So all of those tend to be bad leaving groups. We're not just going to pop off carbon-based groups or hydrogens, and then my other ones just are not. They're pretty strong bases. As is hydride. Hydride's a really strong base, right? It wants to donate that lone pair that it has. Same with my carbanion.